Well, as I said, I've been working with this technology, particularly simulation models, for 25 years, and I've been working with manufacturers in helping them develop systems of excellence, trying to improve efficiencies and making their systems more cost-effective and lean. And in the process, we have used a tool called computer simulation. It's discrete event simulations. And what simulations allows is basically create a computer representation of a real system. And the thing with these simulations is that they allow you to make predictions of how the system will perform, and you don't necessarily need to invest in the actual capital equipment or the implementation of a line. You can use the computer simulation model to be able to determine what's the performance for that model, for that system, sorry. And the thing is that with these computer simulation models, they take time to build. It's a lot of effort in understanding how the system works. And then you have to collect data. You have to analyze the data that it produces, and then be able to make some predictions with it. So to be able to cope on those deficiencies of the simulation model, the digital twin is expected to be a faster solution to be able to make those analysis faster. So what I'm hoping to do today is just to give you an overview of the digital twin and what that is, the capabilities, and also show you a couple of examples and a formula on how to develop the models, and then conclude with some just quick challenges and opportunities for the technology. So the digital twin, as I mentioned, is a digital representation of an object. It could be an equipment. It could be a system or systems of thinking, of systems, like primarily smart cities or some facilities, supply chains. And basically what it's going to do is going to simulate the object and the interactions of that object with other resources or assets in the manufacturing company. Well, what is going to be different is that the physical object will be connected to the digital counterpart almost in real time or in real time. It's going to have engines behind that is going to get the data that it receives, typically from sensors plugging in the equipment or the facility. It gets those data and process it, and it's going to produce a solution, or it's going to produce some prediction. We hope that that prediction is also in near time or real time so that we can make fast decisions. And in the process of making those data analysis, there's going to be machine learning and artificial intelligence engines behind it to do the fast processing of data. Also, what it's going to allow you to do with all the information that it generates, you can provide some feedback, typically in the form of a visualization, which could be an augmented reality or some sort of animation that with this environment is going to allow to interact with the user and make gain a very good understanding of how the physical aspect works. So what you're seeing there is an example of a simulation model, and this particular model is of a warehouse. What this allows us to do is to estimate how many, what is going to be the capacity of this warehouse. And therefore, you can plan what is the adequate size, how many dock ports you should have. What is interesting about this model is that it's not in real time, so you have to do a lot of the manual input of the data, a lot of the data collection beforehand. You have to do some preparation, put it into the model, and then do some analysis. with it. But the key here is that the steps to build these models are also almost a recipe for the digital twin as well. And what you do is you define your problem first. What is the problem that you're trying to solve? Is it going to increase productivity, reduce cycle time, improve the health and safety of your operators, or those kinds of problems? And then you're going to determine what is the system scope. Are you going to simulate or form the digital twin at the equipment level, at the cell level, the factory level, supply chain level? In the process, you have to define what is going to be the level of detail that you want to have. Keeping in mind that as you add more details or more components into your digital twin, what is going to happen is that your analysis time or your computational times will go up. So there is a trade-off on how much detail you want to have and how fast you want to provide your feedback. So at this stage, you are going to decide what kind of sensors you want to install in your system so that you can provide the information in those real times. Hopefully with that, then the digital twin will get some automatic updates as environment changes occur. Then you have the real-time feedback or manual analysis. After you're done that pre-planning step, then you're going to build the digital twin. And there are some commercially available solutions out there. Like the one you're seeing is AnyLogic. There's other commercial available solutions like Simio, Arena, if you're working on the manufacturing space. Each sector will have its own commercially available solutions, but what I have seen most of the time is that companies develop their in-house solution from scratch, okay? Customize it to their needs and equipment level. So at that time, you're going to then verify and validate your digital twin, make sure that it's providing the solutions that you want out of it. And finally, you're going to use it. And at this time, you are going to measure, analyze, improve the data that you provide, that you get out of it. All right, so this is an example that we have developed in the lab. And the problem here that we had is we were trying to look at the number of incidents and injuries in a manual operation. So these manual operations occur very frequently in, let me just go back. These manual operations occur very frequently in areas like Amazon, HEB warehouse, and those kinds of things where there's a lot of these manual operations. Also, at this time, since it's very manual intensive, you want to measure what is the productivity of your workers, how many moves they're doing, if they're doing the exercise correctly or the activity correctly, are they exposing themselves to injuries or economic problems. So that was the problem that we had, and what you're seeing there is a digital twin of this manual operation. It's just a picking, pulling, pushing, pulling operation, just very simple. And over to your right, you see the operator doing the exercise or the activity. And what you see is that the operator is wearing a wearable. It's basically sensors mounted on the chest that keeps track of the biometrics, the heart rate, oxygenation rate, respiration rate. In some instances, you can measure cadence, etc. So that provides the biometrical data. Also, on the side, you see some cameras, and these cameras are motion capture cameras so that you can keep track of the motion of the operator. So you combine all these data together, and what is allow you to do is calculate where is the fatigue level of the operator. Where is it going to reach the critical point that he can not longer do the activity? So if you visit these facilities like Amazon, every day you place your order, and what you're doing there is just you have operators picking and selecting objects from the different locations of the warehouse. And this is actually very tiring. I have seen operators putting together up to 8 different orders at a time. And therefore, they reach a fatigue point. Some of them don't get a break to transition to the next operation, et cetera. So this kind of model will allow you to, get the visualization done, and what you can use is some augmented reality tools so that you can project what is the what other activities you can do. And with these augmented reality tools, what you can do is you can set up some training mechanism for the operator. What you don't see in this particular instance is that these cameras are highly invasive, and they're also very expensive. Each camera costs about $10,000 to produce. So the challenge is, how do we take that from the lab environment to the actual environment, to the actual manufacturing environment? And nowadays we have tools like OpenPose that you can use to plug into your conventional cameras and connect to the system and get the same type of data from these cameras. Also, what you have nowadays is the wearables like the smart watches, Apple Watch. Those are becoming more inexpensive, and therefore they're easier to implement in an environment. And that kind of capability will make the technology that is more easy to adopt for the manufacturers. Also, some opportunities and challenges of the digital twin. This market is about 25 to 50 billion, and it's going to be within the next 5 years. There are many adopters already, typically in the manufacturing, energy, healthcare, and military sectors. Typically, those adopters are big companies, so the technology is harder to implement in the small businesses, in the small companies. So for those particular companies, there's opportunities to have platforms that they can use to build the tools. So applications of the digital twin is the design process. How do you make better designs of your systems? How do you plan the capacity of a manufacturing facility or a work cell? Also, what is the optimization opportunities of the workforce, the life cycle analysis, productivity, and safety? So in terms of technology gaps, I mentioned we have some opportunity to build sensors that are less invasive and that provide the information on real time. There's opportunities to gather data sets so that you can train those artificial intelligence engines so that you can provide feedback back to the operator in a quick amount of time. And then also what kind of platforms where they can build and connect all these different sensors through the Internet of Things. And what we have seen is that the real-time operation, the real-time input collection and data collection is possible in a lab environment, and now we're testing it in actual environment. And then also there's opportunity to train the workforce that will build these digital twins. So just lastly, this is the information. We'll have a tour to the Ingram School of Engineering on Friday. Hope you can join us, and we'll show you not only this project, but other projects that we have available. Thank you for the opportunity, Andres, and thank you for having me.